Welcome in part 2 of radiation effects on CMOS imager. I'm Jérôme Pratlong, Chief Engineer at Teledyne E2V, specialized in visible and infrared detectors. In part 1, we looked at total ionization dose. Today, we will look at the total non-ionization dose, also known as displacement damage dose. This type of radiation can affect the radiometric performance, and especially the signal-noise ratio, but also the performance availability, because it can create dead pixels. In this video, we will look through the basic mechanism, the main impact on imager, but also we will share some key takeaway extracted from silicon results from Teledyne E2V detectors. The displacement damage comes from particles that interact with the material and displace silicon atom. This is referred as the primary knock-on atom. This displacement creates vacancies and interstitials within the crystalline structure. About 90% recombine. However, the rest form stable defect called Frankel pair. Following the dose, single defect can be created, but also cluster or multi-cluster of defects. The main effect on imager is increase in dark current and hot pixels. It can also create random telegraph signals. The test is unbiased, using proton at energy of 40 to 60 MeV. The fluence is based on nil. The dose rate, in general, is around 10 power 7 to 10 power 8. This is much harsher condition than in space, but this is the usual type of constraint for the test. The proton interact with the material, giving an indirect ionization effect that we covered in the previous part, and that is described in the left part of this slide. But it can also create elastic and non-elastic collisions within the lattice, and that causes atomic displacement. We can see that with the turn and the change of orientation of the trajectory of the proton on this drawing. This will affect dark current and noise. On the top left, there is a representation of a pixel, classic pixel 40 type, with here the pin photodiode with the electron collection. And the defect creates an intermediate level between the valence band and the conduction band, enabling some electron to jump from the two bands via these intermediate levels. If the level, as shown on the top right picture, is very close to the conduction band, then electron can be trapped and released randomly over time. The usual representation of a dark current is a frequency log versus dark current. In purple, we've got the pre-radiation simplified representation, where we expect to have a normal distribution with a peak that corresponds to the maximum mean dark current. Post-radiation, however, create a tailing effect here. That is, by experience, meant to be an exponential slope. However, this is not really proven yet. But what is interesting is that it is a direct function of a displacement damage dose and the volume of the depletion. And that are very key parameters. Therefore, this displacement damage can create additional leakage path. Therefore, dark current will be a non-uniformity dark current will be affected. It can create bright pixel, also known as hot pixel, or even dead pixel, random telegraphic signal, and lower CTE for specific type of detector like CCD on CMOS. The average dark current, as I mentioned, and that is the key point, is that is a function of the displacement damage dose and the volume of depletion of the photodiode. In terms of RTS, we've got to differentiate two types of RTS. At the top left, there is a snapshot of a very good paper from Vincent Goiffon, distinguishing the two types of RTS. The first RTS is named here as dark current RTS or DC RTS, and is coming from this level that we've just seen, creating in the photodiode some discrete dark signal variation. There is another type of RTS that is here mentioned as source follower RTS, that is due to the degradation trapping creation in the channel of the source follower, that then will have for effect to increase the noise. At Teledyne E2V, we've already worked on the effect of the source follower RTS by choosing a technology that has a very reduced tailing on this effect via some processing only at the level of the source follower. At the bottom left, we've got a measurement from a Teledyne detector, CIS-120, showing the RTS from the photodiode, but also from the source follower. We can see, if we focus on the green curve, different level, actually 3 of them, of different amplitude, A1, A2, A3. This is 3 types of defects that create different variation with different amplitude. On each level, we can see here or here some quick variation that represent or is the RTS from the source follower. This means that the important point there is we got 2 types of RTS, one from the source follower, one from the photodiode that we call dark current RTS. The source follower RTS will contribute on the noise floor, but can be largely reduced by using correlated double sampling technique. The dark current from the photodiode, the dark current RTS, will contribute to the dark current DSNU and the hot dead pixel. It is to be noticed that the dark current RTS can have multi-level. The signature can be different per pixel. And again, this dark current RTS will be a function of the depletion volume and the dose of the test. These effects can be reduced and controlled by temperature if it's possible in the application to cool to low temperature. Now, we are going to go through a few examples showing the variation of the effect on dark current following volume of the depletion area and the dose of the test. Here, it's 2 examples of a device, CIS-107, is a 7 micron-pixel pitch with 2 variants. One had a standard resistivity material, which has for effect to not enable a large volume of depletion. And the same device processed on a high resistivity material where the depletion volume is much greater. And we can see that directly on the proton damage effect. We've got the tests were done with the same dose, same pixel, but a depletion of 4 times bigger for the high resistivity material. And we can see that the dark current has increased by 4 times. Therefore, this relation is something we see also on silicon. In a similar approach, we looked at CIS-107 and CIS-120, also known as Capella, where the difference between the two is only the dose, with 2 times higher for the CIS-120, similar depth or volume of the depth of depletion. And we can see again that the dark current is 2.5 times higher for the CIS-120. Therefore, we have also seen this relation between dose and depletion volume on the dark current post-radiation. Therefore, now if we look at post-annealing, we can see that post-annealing, we can have a large recovery, which is about 50% for any fluence we looked at, between 5x9 to 2x10. Therefore, annealing is an important test to do, since it's more realistic and we can see a great recovery from the damage caused by radiation. We also did some experiments on what we call aero technology. The aero technology differs from the standard technology by the fact that we have a mean to apply a negative voltage at the back of the detector, and that enables to get even larger depletion, hence higher volume of depletion. And the test, if we compare to the CIS-120 with a similar pixel but on aero technology, we see that we've got an increase that is about a factor 8. And when we looked for the same dose, the difference in terms of depletion, we see again this number where the CIS-220, which is the aero version of the CIS-120, has a volume of depletion 8 times the CIS-120. Therefore, again, we see the effect of the volume of depletion on the post-radiation results. In terms of RTS, same if we compare the CIS-120 and the CIS-220 with 8 times more volume of the depletion, we can see an increase on RTS numbers as expected. But also here, we've shown that going from 20 degrees to 3.5 degrees, which is not very low, we have a very important reduction on the RTS number. In terms of takeaway, the impact of a total non-ionization dose is mainly affecting the dark current, DSNU, and creates hot or dead pixels. It depends on depletion volume, it depends on the dose, and it depends on temperature. Therefore, displacement damage is not really something we can do about in terms of design, apart making sure that we've got the minimum depletion volume needed for the application. We can minimize the source follower RTS by using ultra-low noise transistors, but also correlated double sampling. Low temperature is a way to mitigate for these effects. And for aero technology, obviously, dark current, DSNU, and RTS will increase with the increase of the volume of depletion. In the next video, we will look at the single event effect, also known as heavy ion radiation, again looking at the basic mechanism, impact on imager, and some takeaway from our silicon results obtained from Teledyne 2V detectors.